Hi, in this video we're going to continue with Chapter 5, Polynomials and Rational Functions, and we're going to focus on Section 5.2, Power Functions and Polynomial Functions. Now, some of the things that we will be doing in this section is we will be identifying powers, identifying end behavior of power functions, identify polynomial functions, and identify degree and leading coefficient of polynomial functions. So let's first start with talking about what is a power function. So a power function is a function that can be expressed in the form f of x equals k to the p, where k and p are real numbers and k is known as the coefficient. So the number in front of x, we call that the coefficient. So we start right off the bat with an example identifying power functions. Which of the following functions are power functions? And if you'll look at this list, you may recognize our toolkit functions from chapter 3. So we have the constant function, the identity function, the quadratic function, cubic function, reciprocal and reciprocal squared, square root, and cube root functions. So looking at these, which ones do you think are power functions? So you could probably recognize that f of x equals x squared is something in this form. In this case, the p is 2. K would be 1. You probably also recognize that f of x equals x to the third is a power function, where p is 3 and k is 1. But what about the others? They don't look like power functions, so maybe we should just say, nah, they're not. But actually, they are. You can write every single one of these functions as a power function. So let's see how that works. So for the first one, f of x equals x to the 1, f of x equals 1, rather, we could write that as f of x equals x to the 0, because if you will remember any of your rules of exponents, x to the 0 is 1. So that means that f of x equals 1 is in fact a power function. What about f of x equals x? So for this one, we could write this as f of x equals x to the first power. F of x equals x to the 1. So that is a power function as well. And you may be wondering, how do we write these fractions, the reciprocal functions, as power functions? Well, you can, and this is how. Maybe you will remember from exponents that if you have a fraction, whatever is in the denominator, you can bring it to the numerator by making its exponent a negative. So f of x equals 1 over the x is the same as f of x equals x to the negative 1. So that is a power function. And then for reciprocal squared, then that means f of x equals x to the negative 2. So that is also a power function. That brings us to the square roots. How can those be power functions? They're locked in those little square root boxes, but they definitely are power functions. And this is how. When you have a square root, it's the same as having the base that's underneath the square root sign, the radicand, and carrying it to the fraction power, so 1 over whatever the root is. So f of x equals x squared is the same as f of x equals the square root of x. And then that means that this last one, f of x, is equal to, the cube root of x is the same as f of x equals x to the 1/3. So there you have it. We can write all of these as power functions. So all are power functions. So your turn. Try it. Which of these functions are power functions? So pause the video and decide whether they're power functions. Here's a hint. You may have to rearrange some of these, as in simplify them, to see if you can get them into the k times x to the p form, and then decide whether you think they are power functions or not. Okay, so hopefully you paused the video and you had a chance to try to work these. So the first one, if I simplify this, if I do the multiplication, 2x times 4x to the third, I get 8x to the fourth. Because you remember, if you multiply variables with exponents, you add the exponents if the bases are like. So this is a power function. However, this next one, you can't add negative x to the fifth plus 5x to the third. They're not like terms, so we can't get that into the correct form. Also, with this one here, f of x equals 2x to the fifth minus 1 over 3x squared plus 4, that one we can't simplify either. So neither one of those are power functions. All right, let's talk about end behavior of power functions. Okay, so let's check out these graphs that we have at the top. So on the left-hand side, we have f of x equals x to the sixth, g of x equals x to the fourth, and h of x equals x squared. What do you notice about all three? Well, one, all three make something that looks like a parabola. But what do you notice about their exponents? All three of these exponents are even. And so this slide, we're talking about end behaviors. So what's going on at the end of the graph, so where the arrows are? So what it looks like to me is that if you have an even function, it looks like the arrows are pointing in the same direction. And just think about, if we had h of x, if we change this to negative x squared, it's still a parabola with the arrows pointing in the same direction. It just points down. So if you have an even power, we can say that the end behaviors point in the same direction. Whereas, look at the graph on the right. Each of these graphs have an odd power, an odd exponent, and notice the end behaviors. On the right side is going up, and on the left side is going down. So the end behaviors are opposite. So end behaviors over here are the same, and then end behaviors over here are opposite. Okay, so if we're given a power function f of x equals k x to the n, where n is a non-negative integer, so this is only for positive exponents, identify the end behavior. First, you need to identify whether the power is even or odd. And that is going to tell us whether the end behaviors are pointing in the same direction. Now, the next thing that we need to look at is whether the constant, the k, is positive or negative, and that's going to tell us something else. So I'm going to go to the next slide for that. Now, once we figure out these behaviors based off of the exponent being even or odd, and then the positive or negative constant, that will tell us everything we need to know about the end behaviors. So if we go to this next slide, this chart tells us about whether the constant k is positive or negative. Now, I did notice that there is a typo on here, but I'll show you that. I will correct it when we get to it. So if you have an even power, if the k is positive, then the graph is going to point up. It's going to open up. So, and that makes sense. It's like saying, instead of the k, the coefficient being k, we could say it's a, right? So when we had ax squared, if a was positive, it opened up. If a was negative, it opens down. And then in that case, both of the ends are pointing in the same direction. So if the k is positive, because we're not using a here, but I just want to show you it's the same thing. If the k is a positive, the graph opens up, both ends pointing in the same direction. If k is negative, it points down, both ends pointing in the same direction. So how would we write this algebraically? So algebraically, we would say for this even power at the top, you would write it twice. You would write as x approaches negative infinity, what is happening? So as it's going to negative infinity, the f of x is going up. So the f of x is also going, well, actually, the f of x is going to positive infinity. So as x goes to negative infinity, f of x goes to positive infinity. Now what happens as x goes to infinity? So as x goes to infinity, it looks like the f of x is going up. So as x is going to infinity, then f of x is also going to infinity. Now let's look at the bottom one. As x is going to negative infinity, x goes to, this is a typo, this is one of the typos I was referring to. This should say x is going to negative infinity. So just looking at it, I just want to show you as x is going to negative infinity, f of x is going down, so it's going to negative infinity. As x is going to positive infinity, x is also going to negative infinity. So this one was written correctly there. So for the odd powers, what does that mean? So the way I look at the k is the k determines the right end behavior. And then if you figure out the right end behavior and then use the fact that it's even or odd to determine the left behavior, so it's either going to be pointing in the same direction or opposite, then you know both sides. So if k is positive, it's going to open up on the right. And if k is negative, it's going to open down on the left. And that's the same thing that went on here with the even powers. The difference is when it's an odd power, then the left behavior is going to do the opposite of what the right behavior is doing. So for the odd power, as x is approaching infinity, the f of x is also approaching infinity. So this should say, this should say, as on the bottom one, as x approaches infinity, f of x. As x approaches infinity, f of x approaches positive infinity. And there was a little, a light, like negative sign there, and that was incorrect. So as x approaches infinity, f of x also approaches infinity if k is positive. As x approaches negative infinity, f of x approaches negative infinity. Okay? So, let's look at this one. As x approaches negative infinity, f of x approaches infinity, positive. So this was a major typo on this PowerPoint. So I'm fixing that. And that's if the k is negative. And as x approaches infinity, f of x approaches negative infinity. Okay, so you can use that chart to help you. I usually kind of just draw it out, and that helps me to figure out what the end behaviors are. So it says describe the end behavior for f of x equals x to the sixth. So the first thing that I'm going to do is I'm going to determine the k and the p. So in this case, the k is 1. That's positive, which means that the right in behavior is pointing up. And then the p is 6. That's even. That means that the left in behavior points the same direction as the right in behavior. Because they're even, that means they point in the same direction. So what does that mean for the in behaviors? Well, as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, what is happening with the f of x? It's also approaching infinity. So when you do these, when you're checking your work, if it's even, your f of x's should be both going to the same infinity. All right, so let's look at this next one. F of x equals negative 1 x to the 7th. So in this case, k equals negative 1, p equals 7. So we have a negative and we have an odd. So first, let's look at the negative. So the negative tells us that the right behavior opens down, and then the odd power tells us that the left behavior points in a separate direction. So it's going to open up on the left. So as x is approaching negative infinity, then f of x is going where? It's going up. It approaches infinity. On the right side, as x is approaching infinity, f of x is going down. So it's approaching negative infinity. So you guys pause the video and do this, try it. Describe in words and symbols the in behaviors of f of x equals negative 5x to the 4th. Okay, so we have k equals negative 5, so that's a negative, and x equals 4. I'm not sorry, x equals 4, p equals 4, so that is even. So we know they both point in the same direction, and the right behavior for a negative is pointing down, so they're both going to point down. So as x is approaching infinity and negative infinity, f of x for both of those is approaching negative infinity because it's going down. So as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x also approaches negative infinity. All right, so we're going to stop the video here, and we will pick up with the next slide in part 2.